So hi guys, we're machine learning for traffic behavior analysis in smart cities. This is our team. My name is Haejin. I'm a rising senior in Rutgers, and I'm studying electrical computer engineering and computer science.
Hi, I'm Dominic. I'm in the class of 2026 at Stevens Institute of Technology, and I'm studying computer science and math.
So when analyzing traffic behaviors in large city environments, vehicles aren't the only thing that needs to be taken into account. Pedestrians add a level of complexity that makes it difficult to test algorithms in the real world. So why should we care? When testing autonomous vehicles, especially in a city environment, pedestrian safety is not a guarantee. In order to continue advancements in road safety and autonomous vehicles, there needs to be a robust virtual environment to conduct experiments. So the goal of our project was to create an environment that is able to run experiments in Carla and implement/test multi-agent reinforcement learning algorithms used to collect data on traffic behaviors. So this includes setting up and connecting physical tools, creating a digital twin map, implementing a multi-agent reinforcement learning algorithm to Carla, and evaluating the algorithm's performance. So what is Carla? Carla stands for Car Learning to Act, and it's an open source driving simulator with customizable scenarios. So this means that you can control traffic behaviors, pedestrian movement, and vehicle movement through scripts, steering wheel and gas pedal input, or keyboard input. There's also a Python API for the configuration of the environment, so you can collect camera and sensor data and use autonomous driving scripts. And you can also implement and use the maps that are already available with Carla, or create your own to use your own experiments.
Yeah, so to actually set up and connect the physical tools, we set up Carla at the core building, which is on Rutgers main campus. We originally had it all set up here, but we needed to move over there because we needed a better computer to run our algorithms on. And then to connect the MetaQuest 2 to Linux, Linux doesn't support the MetaQuest, so we had to use ALVR, which is an open source bridge between Linux and SteamVR. And then we just use Lenovo software to connect the steering wheel and pedals.
So we also had to create a digital twin map. So what is a digital twin? In the simplest definition, it's a virtual representation of a physical object. So if you look at the top right corner here, you can see that there's a digital representation of an intersection that's located in New Brunswick, which is just a couple of minutes north of the lab. And we use this intersection because it has cameras and sensors fitted into it in the real world that our advisors have access to have access to the data. And if you look at the bottom right corner here, this is a map representation of the same intersection through OpenStreetMap, which is a website that contains map data that can be then imported into Carla using the digital twin tool provided by Carla. And there's a lot of issues that we came across when using this feature, because it's still a very experimental feature. So sometimes the ground wouldn't generate correctly, the roads wouldn't generate fully, and objects would be placed in the wrong places. So this involved a lot of trial and error in order to overcome these issues, and adjusting the XODR file, which is a file that's generated when creating maps in Carla that contains the actual data of like these objects and buildings and roads that we use to put objects in the right locations and fixing just minor issues with the map. And if you look at the bottom left corner here, you can see that there are colored lines that represent waypoint routes, which are predetermined routes that vehicles can follow in order for us to test our algorithms and also compare results.
Yeah, so to actually implement a multi-agent reinforcement learning algorithm to Carla, we first need to create a Carla environment. And this pretty much just means we need to set up the amount of cars for the number of agents that we want, and then attach sensors such as lane invasion sensors and collision sensors to these cars. And then to implement the multi-agent code to control the cars, in our case, we use MAPO, which is multi-agent proximal policy optimization. You need to just implement your actor and critic networks and then hook them up to the environment. And then we just want to evaluate the algorithm's performance. And to do that, we're going to look at the loss function, which is down here. You see it starts high and gets lower over time, which is good. And this is pretty much the difference between the expected reward given a state in action versus the real reward. And then our reward values, which are at the top, it starts low and goes up higher too, which is good. And you can see it fluctuates a lot, and that's because the algorithm is taking random actions to explore its state. That'll even out over time. And then we just want to measure how close it is to the optimal route. So some future plans for this project would be to optimize and fine tune the algorithm to get better performance. And this pretty much means we want to change the hyperparameters like the epsilon decay values. And we could also implement frame skipping so the networks don't have to update so much. We want to implement different multi-agent algorithms and create different scenarios and digital twin maps. So right now we only have 2 digital twin maps, which is the New Brunswick and New York intersections. And we only have one scenario, which is the intersection. And then we just want to collect data from the human interaction. Since this is a real world map, we're hoping that some of the state and actions here will actually translate to the real world.
We just wanted to thank Professor Ortiz and our advisor Sonia for their guidance and support in our project, and also thank WINLAB for their support for this internship program. Thank you.
Any questions? Thank you, guys.